All right, everybody. So like I said, I've been seeing a lot of patterns, and this is what I've been seeing, and this is the theory I put behind it. Okay, here we go. It's going to be like a 1986 presentation here with pencil and paper. And believe it or not, this took me many rounds to draw these pictures. Anyways, keep up. If you need to pause and come back and look, do it. This is what I see. We're going to try to keep this video short, guys. Okay? This is a brick. A single brick. One brick. We all are aware of bricks. Okay? One brick. Did I lose anybody yet? I don't think so. A brick stores energy. It's comprised of nodes. I'm going to use that term nodes for lack of a better term. I don't know if that's right or not. We're going to call these nodes. There's a terrible drawing on the top of a 3D brick with 4 nodes in it. They look like soda cans. There might be 8, there might be 12, there might be more, there might be less. This is what I'm seeing. There's also smaller nodes around the outside edge of the brick. The entire brick is comprised of nodes. It's storing energy. This is a close-up of one node. It looks like a soda can. It stores energy. The entire realm is made of these, was made of these, is still made of these. When the X Factor began, and the X Factor process began, these nodes started bursting and overloading, okay? And they started rotating. This is what a single node, the last picture we just showed, the soda can looking thing, when one node explodes, it looks like this. This is the pattern I'm seeing everywhere, in all of the evidence, everywhere, in more places too. This is a single node exploding, okay? When a single node explodes, all the other nodes around it are also going crazy and exploding, and they're all connected. Every node in the realm is connected. All of them, every single one is connected. When that single node bursts, it starts connecting with other nodes around it. And this is the main pattern that I've been seeing that is driving me crazy. I'm seeing this pattern everywhere. And when I mean everywhere, I mean everywhere. It's on the macro. It's on the micro. It's everywhere in between. The pattern is infinite. See the pattern? Now really, this pattern is just part of a bigger pattern. That pattern is just one of these on a bigger pattern, on a bigger node, a larger node, okay? Bigger node, connecting everything. Everything's rotating and spinning, okay? And churning and absorbing the matter around it. Now, when you have a large brick wall, it's all brick. If you have nodes evenly spaced throughout the brick wall, when the X Factor event began, everything started rotating and churning and connecting and absorbing. So you have nodes evenly spaced throughout a wall, and what they're doing is they create a parameter around the node, and it will rotate within the node, within the boundaries of that it's created next to the next node, okay? And your brick wall, it will create perfect blocks, granite blocks, limestone blocks, sandstone blocks, whatever kind of blocks you want, it will create. Now, when you have a plain brick wall with nodes everywhere, and the X Factor process begins, now you have a bunch of granite blocks. The green lines represent granite blocks, okay? They've been noded out. They've reached, so they've gone up and down, left and right, as far as they can. Now, sometimes you'll see granite with the rough edges. So it's gone as far up and down as it can. It's gone as far left and right as it can. And now it's expanding depth-wise. And this pattern will become 3D. It will start expanding. This is where expansion comes from. That pattern will turn into almost like a 3D donut made of that pattern. And that 3D donut, guess what? It's part of a bigger 3D donut. And that's your expansion. We'll get into that later.
3D printed donut versus real donut.
Here's our granite wall. Or it's now a granite block wall. It used to be a brick wall. Because of the nodes and the churning and the rotation and the absorption. And the walls created is now a granite stone wall. Now, like I said, they're all connected. The small nodes connect with the medium nodes connect with the next nodes, and the next nodes, and it's infinite. Massive nodes sometimes are exploding. Massive, you guys understand massive? This is what a giant node, like on the side of a mountain, on the bottom of a mountain, or in those kind of areas, you'll see a giant node exploding, rotating, churning, absorbing everything around it, acting in the exact same manner as the smaller nodes. It's doing the same thing. It's the same process on a bigger scale. If you've ever been in a chat room with me, you may remember me mentioning that Meltology or brickology is very similar to a stereogram. It's also called a magic eye. This is the image that if you stare at it long enough, you will see another image within it. So what do we have here, ladies and gentlemen? We have a bunch of cute little bunnies, right? But if you stare at it long enough and unfocus your eyes, what are you going to see? You're going to see this minivan. And once you see the minivan, that's the only thing you're going to see whenever you look at this image, okay? So I'm pretty sure everyone in this community understands that concept, okay? This pattern is very similar to that concept. Once you see this pattern, it will blow your mind because it's everywhere. Here we go. Again, here's our single node, our soda can looking node within the brick, okay? It is my opinion that that plus sign on the top starts rotating and absorbing in a pinwheel fashion the brick lines around it, pulling the brick line into the top of the cylinder, rotating, churning, and regurgitating another form of matter out the other side of the cylinder, granite, limestone, etc. Okay? Just a little reminder. Now that being said, I'd like to propose a 10,000 mile building, brick building, up and down the west coast, from the top of Alaska all the way down to Mexico. When you have these giant nodes exploding, what it's doing is it's sucking everything down into it and rotating. So I want to propose a 10,000-mile building with gigantic nodes, evenly spaced in between, that when the X-factor process began, they start bursting and overloading and churning and pulling down the top of the building, creating a mountain landscape. Huge nodes pulling down. I think in the middle, in these valleys, a lot of times you're seeing it and you'll see a big boulder. It's the node. It has pulled down the building down to that section. Massive. This is the macro. It gets much more macro than this, but this is macro for now. I'm proposing this idea.
If one was to build a building that is 10,000 miles long, 2 stories tall, 75 feet deep, with a dividing wall every 30 feet, including doors and windows, and a second floor, how much materials would be required to create these buildings out of red brick? With the brick being fired in kilns, and using horse and carts to transport, and let's say around the early 1900s. And can you give the logistics of this operation and the cost?
Designing a 10,000-mile-long, 2-story, 75-foot-deep red brick building in the early 1900s, with dividing walls every 30 feet, doors, windows, and second floors, transported by horse and cart, is one of the most ambitious hypothetical industrial challenges imaginable, far beyond any historical precedent. Let's break this down into quantities, logistics, and cost, approximating everything in line with early 20th century American capabilities, circa 1900 to 1915, and using known historical data, e.g., brick sizes, transport capacity, labor costs. Physical specifications. 1. Total building dimensions. Length 10,000 miles equals 52,800,000 feet. Depth 75 feet. Height. Assume each story is 12 feet, 24 feet total. Volume of wall envelope. Only outer walls plus dividing walls considered for simplification. Hash materials needed. 2. Bricks. Assume standard brick size equals 8 inch by 4 by 2.25 inch. Bricks per cubic foot equals 14.3. 1,000 bricks equals 1 ton dry weight. Hash A. Exterior walls only perimeter, assuming 4 walls, ignoring floor roof for now. Front plus back walls equals 2 kinds of 52,800 feet. Sides equals 2 and 75 feet. Total wall length equals 105,600 and 150 feet. Height equals 24 feet. Thickness equals 1 feet. Single width plus interior finish. Volume equals 105,600 and 150 feet times 24 feet as 1 feet equals 2.534 billion CQ feet. Bricks, 2.534 BQ feet times 14.3 bricks equals 36.2 billion bricks. And now charter B. Interior dividing walls, 52,800 feet, 30 feet equals 1.76 million walls. Each 75 feet deep, 24 feet high, 1 feet thick. Volume equals 75 times 24 10 ones, 1.76 men's, 3.168 billion QQ feet. Bricks, 3.168 B, 14.3, 45.3 billion bricks. C floors, second story support. Assume 75 feet times 30 feet, 1 feet floor slabs, 1.76 menor sections. Volume equals 3.96 billion CQ feet. Brick, vaulting or terracotta floor arches, 56.6 billion bricks. Total bricks needed, 138 billion bricks. 3. Transport horse and cart. Typical cart haul equals 1 ton, 1,000 bricks. Total trips needed, 138 billion per 1,000 equals 138 million cart trips. Each horse cart round trip equals 20 miles per day average, including loading. 10,000-mile building likely built in segments, so supply distributed from regional brick kilns, say every 50 miles along the length, equals 200 kiln zones. Each zone needs to move. 138B, 200 equals 690 million bricks, 690 m trips equals 3,450,000 trips per zone over, say, 5 years, equals 1,890 trips per day per zone, about 2,000 horses and carts per 50-mile zone. Brick production. 4. Kilns and firing. Clamp kilns, 1900 tech, 50,000 bricks week per kiln, 690 mem bricks per zone, 50,000 equals 13,800 kiln weeks. If 100 kilns per zone, 138 weeks, per 2.5 years per zone. Total kilns needed across 200 zones, 20,000 kilns. Each manned by 4 to 6 people, 80,000 to 120,000 brickmakers. Cost estimates, 1,900. 5. Brick costs. Average 1900 cost per 1,000 bricks, 1/6 of 50 has 138 billion bricks, $1,006.50 equals $897 million. Hash 6. Transport costs. Hauling per 1,000 bricks, 20-mile round trip, $1 total, 138B, y 1,000 times equivalent is $138 million. Harp 7. Labor construction, assume $50 per hour wages. Estimated 500,000 laborers working over 10 years. 300 days per year, times 10 hours a day, times 10 years, 30,000 hours. 500K, 30,000 times 50 equals $7.5 billion labor. Act total estimated cost, early 1900s dollars. Item, estimate. Brick material, $897 million. Horse transport, $138 million. Kilns and fuel, $150 million. Construction labor, $7.5 billion. Tools, mortar, scaffold, $100 million. Roads and logistics, $200 million. The total estimated cost of building a 10,000-mile-long, two-story red brick building in the early 1900s, including materials, labor, transportation, kilns, and infrastructure, would be approximately, open quote, $9 billion. That's $9,000 in early 1900s dollars. Close quote. To give you a sense of scale, adjusted for inflation, that would be roughly $300, $350 billion in today's money. 2025 USD. It would have exceeded the entire GDP of the United States at the time by several times over. To put that in perspective, the Panama Canal, 1914, cost about $375 million, and the entire U.S. federal budget in 1900 was about $500 million. Feasibility. Workforce. 1 to 2 million workers sustained over a decade. Brick production. 20,000 kilns active. Constant fuel and clay supply. Transport. Roads, horses, carts maintained constantly. Living logistics. Mobile camps, rail spurs, food supply chains needed. Insane scale. Would be the largest construction project in human history by a factor of at least 100. Hash scale comparison. Length 10,000 miles equals 2.5x Earth's diameter. Bricks, enough to build a Great Wall of China. 3x over. Horse trips, 138 million equals 5,000 years of cart hauling at 75 trips day.
Are there any land masses on Earth that are at least 10,000 miles wide?
No, there are no land masses on Earth that are 10,000 miles wide in any direction. Here's the reality. Earth's maximum measurements. Earth's circumference at the equator, 24,901 miles, 40,075 kilometers. Earth's diameter, widest point, 7,907.5 miles, 12,742 kilometers. So even if you built something all the way around the planet at the equator, it would be just under 25,000 miles long. But no landmass itself spans even half of that. Largest landmasses, for comparison, landmass, max width, approx. Eurasia, Europe plus Asia combined, 6,200 miles, 10,000 kilometers. Africa, 4,600 miles. North America, 4,500 miles. South America, 3,300 miles. Australia, 2,500 miles. Even Eurasia, the largest continuous landmass, is only about 6,200 miles wide, which is 3,800 miles short of your 10,000-mile target. Close quote. So, where could a 10,000-mile building go? The only way a 10,000-mile-long structure could exist on Earth is 1. Winding across multiple continents, or 2. Circling the Earth, like a ring around the equator, theoretically, or 3. Following coastlines or specific latitudes in a continuous line.
What exactly is a node when we talk about a node when referring to a circuit? So we're going to go over some textbook definitions here, which I've written out in advance so you don't have to watch me write them. A node is the junction of two or more branches. Okay, great. Well, what is a branch? A branch is any portion of a circuit with two terminals connected to it. Okay, great. What does that mean? So, for example, if we draw our usual very simple circuit with just a battery and a resistor, well, I would say that this circuit has two branches. So anything where you can draw a bounding box around part of the circuit, and then there are two external terminals to connect to, and that is a branch. So the battery itself is also a branch, and a node is a junction of two or more branches. So I have a node there and a node there, where one branch meets another branch. I have two nodes in this circuit. Node and node. And as you connect more stuff in series, this is usually pretty easy to deal with. So for example, we're going to have our battery and a circuit with two resistors in series. Now note that I could define each individual resistor as a branch here, because each one has those two external, if I can pronounce that, terminals to the rest of the circuit, or I could define kind of a bigger branch that encompasses both of those resistors, and then again has those two external terminals to connect to the circuit here. So if I went through this circuit and labeled each node where two parts are connected, or two branches are connected, I could call it node A, node B here, and node C down here. Usually when adding things in series, that isn't much of a problem. Where people tend to get tripped up is when things are drawn in parallel based on how circuit diagrams are drawn, especially because some textbooks or websites might use dots to indicate where wires join. So they don't all do this, but some do. I usually don't bother doing it when I'm sketching the diagrams, but you might see things that use a little dot that's slightly thicker than the rest of the line to indicate when two wires join like this. And your instinct is to look at that and think, oh, that's a node, and this is a node, and these are somehow all different nodes. And that is not correct, okay? Remember that in a circuit diagram, these lines just represent zero resistance wires. Okay, so if you want to label this, oh, that's node A, and that's node B, and that's node C, and that's node D, and this is node E, F, G, H. Okay, that is not correct because all of these points are electrically equivalent. That is actually all just one node. Call that node A. Okay, and this is all just one node because all of those points are electrically connected. They're just directly connected by zero resistance wires, so that is just node B. If it helps, and this is what I had on the first slide, kind of went over very quickly, you could also just redraw this circuit like this, where you have physically a single node up there. Remember, you can go back to the video on circuit diagrams and how you can change the physical layout of the diagram without changing the electrical connections. So if it helps you to visualize it and understand why that circuit only has two nodes, then you can draw it like this. So there's node A and there's node B. I could define all four of these resistors in parallel as a branch because it only then has two external connections to the rest of the circuit. And you can still treat each individual resistor as a branch. But again, those nodes are not actually separate things. So if I look at these two resistors and say, okay, well, this one has a connection there and this one has a connection there, again, those are electrically equivalent because they're just directly connected by zero resistance wires. So be careful. Don't get tripped up when people start applying Kirchhoff's current law, which we're going to see in the next video. People can get tripped up in circuits like this and start kind of trying to apply that to each junction here, where you look at the currents flowing in and out of each one of these lines at each one of these intersections, and that kind of becomes redundant. What you really want to do is look at it like this, where you're only analyzing that single node.
Say woof again! Say woof again!
I've got one that can see.
This is my kung fu, and it is strong.
See you later.